All right, so for section 5.3, we're going to be looking at logarithmic functions and their graphs. And I want to show you how logs were created, basically, to be the inverse of exponential functions. So we're going to use that in such a way that logs undo exponential bases undo logarithms. Okay, so first let's look at what they look like and some of their properties. Logarithmic functions look like this. F of x is equal to log base a of x. Now, this is specifically base a, where this is a positive number not equal to 1. Very similar to exponential, right? So this base is going to vary, or your graph is going to vary dependent on what that little base number is. Okay, there's two very common logs that we use. And we like using them because we have calculator buttons for them, which is the log button and the ln button on your calculator. So the log button is what we call the common log, and that's log base 10. And usually when we are talking about the common log, log base 10, we just write log x. So if you don't see a little subscript number, it's an implied 10, okay? The other one is our ln, which is our natural log. Natural logarithms are log base e. So instead of writing log base e, we're just going to write ln of x. Okay. Now, I don't mind if you want to use log base e to help you solve a problem, but just make sure you know log base e as the natural log. Okay, it's the same thing as ln. Okay, why we care? Here's why we care, people. Because a log and an exponential function has an inverse that is log with the same base. So if I have a to the x as an exponential function, what would undo that is log base a of x. Or if I start out with log base a of x, then its inverse would be a to the x. Okay, so what that means is that they undo one another. Just like a square root undoes a square undoes a square root, right? So let's look at some of these. I'm actually going to skip down to this. We're going to start at the bottom here. So what this means is that if I have an exponential base a, and I have a log base a up in that exponential's exponent, those will actually just cancel, and we would just be left with whatever's inside that log, okay? So if I have an exponential base a evaluated at log base a, those cancel, just like a square and a square root, okay? It also works the reverse way. If I have log base a, and inside my log base a, I have a to the x, then log base a and a will cancel. And again here, I'm just left with x. So I'm just left with whatever was in the exponent there because these cancel. So I can kind of extend this rule to any power of a. So notice here I have log base a of a, and its exponent, it would be just an a to the first power. So anytime I have log base a of a, those would cancel, and this would just equal 1, right? And then I would want to do the same thing here. I'd really like to be able to cancel this log base a, but the only way I can do that is if I have a to some power on the inside. So notice the only power of a that would equal 1 is a to the 0 power. So this is the same thing. It's log base a of a to the 0 power, right? Because anything to the 0 power equals 1. Now we can cancel our log base a, and this would just be 0. Okay, so these are some helpful properties that we're going to use to simplify logarithmic or exponential expressions, knowing that if I have a log with an exponential inside of it where the bases match, they cancel, or if I have an exponential function that has a log with that same base in its exponent, those cancel. So let me show you some. That's going to be our goal, is to try and write these with the same exponential base and the same log base so that we can cancel them. So if I look at this first one, log base 2 of 4, my log base is 2, so I'd like to write this as an exponential base of 2 to some power. And we know that 4 is 2 squared. So I can rewrite this as log base 2 of 2 to the second power. And then my log base 2 and 2 will cancel. So this just equals 2. Okay. Same thing on this next one. I have log base 3. So I'd really like to be able to write that 1 as 3 to some power. And the only way that I can raise 3 to some power and have it equal 1 is if I do 3 to the 0 power, right? Now my log base 3 and 3 will cancel, and I'm left with just 0. Okay, let's look at a few more. On this next one, I have log base 2 of 1/2. And what I really want is log base 2 of 2 to some power, right? And right now my 2's in the denominator, and I have an exponent of 1, right? I can't cancel it right now because the 2's in the denominator. So if I want to move this up to the numerator or flip it, I can do that by changing the sign of the exponent. So in other words, I can write this as log base 2 of 2 to the negative 1 power. Because if I move that 2 across the fraction line or flip it, right, that changes the sign of its exponent. So it's a positive 1 exponent in the denominator. If I flip it to be in the numerator, then we're going to have a negative exponent, right? So log base 2 of 2 cancels, and I'm left with negative 1. Okay? Let's look at the next one. We have log base 3 of 27. We'd really like this to be log base 3 of 3 to some power, and we know that 27 is the same as 3 cubed. Okay, so now my log base 3 and 3 cancel, and I'm just left with the 3 that was in the exponent. All right, let's look at another one. Let's look at this one. Okay, 81 is a power of 9, so that's good. So let's go ahead and rewrite this. Log base 9 of 1 over 81 is 9 squared. But I can't cancel right here, right? It has to be log base 9 of 9 to some power, not 1/9. So again, I want to take this and move it up to the numerator or flip it. But if I flip it or move it across the fraction line, that changes the sign of the exponent. So this becomes log base 9 of 9 to the negative 2 power. And then log base 9 and 9 cancels, and that leaves me with just a negative 2. Okay. All right, let's look at 2 more. Now notice on this one doesn't have a log base. So when there's no base written there, remember it's an implied base 10. So what I'm hoping for is to be able to write this as log base 10 as 10 to some power, right? That way my log base 10 and 10 will cancel. So I have to figure out what power of 10 is this decimal. So I'm first going to change this decimal into fraction form. So remember, good old place value, right? My first place value is the tenths, right? The next place value is hundredths. Can't spell, right? Then the next place value would be thousandths. And then the last place value here would be 10 thousandths. Right? I remember doing that way back when. So what this is saying is that we have 1 10,000ths. So I can rewrite this as log base 10, and we have 1 10,000ths. Right? Now the good news for us is that 10,000 can be written as a power of 10. So this becomes log base 10, 1 over 10 to the, if you're not sure, just count the zeros. 1, 2, 3, 4. So this is 10 to the 4th. And then I still can't cancel because this all just has to be 10 to some power, not 1 over 10 to some power. So I need to move this up to the top or flip it, right? We move it or flip it, changes the sign of the exponent. So this becomes log base 10 of 10 to the now negative 4. So log base 10 and 10 cancel. This just becomes negative 4. Okay? All right, let's look at one more, and then I'll have y'all try some. All right, so this is ln. This is our natural log. Remember, natural log is base e. So what we'd really like to have is log base e of e to some power, right? Or ln of e to some power. That way these cancel. So I need to be able to write this as e to some power. And right now it's written in radical form. So remember, we can change it from radical form to fraction exponents by doing our power over our root. Okay, so to go from radical form to writing it with a fraction up in our exponent, we just have to write the power over the root. So the power, or the multiplicity, the number of copies I have of e, well, this is just e to the first power, right? And then I'm taking the fifth root of it. So my power is 1, my root is 5. So that means that I can rewrite this as ln of e to the 1/5 power. Okay? So just taking it out of radical notation and writing it with a fraction exponent. And then because ln is log base e, right, ln and e cancel. And this just gives me 1/5. Right? Okay, so on the next page, there's 4 for y'all to try. So I want you to go ahead and pause the video, simplify those as much as you can. If you get stuck or ready to check yourself, play the video, go over them. Okay, so on the first one, we can rewrite 8 as 2 cubed, and then log base 2 and 2 cancel, so this just equals 3. Okay, 1/3, we should be able to write 1/9 as 1/3 to some power, because 1/9 is what you get if you square a third, right? So we can replace 1/9 with a third squared, and then log base 1/3 and 1/3 cancel, and we're just left with the 2 from the exponent. Okay, on this one we have ln, so we want it to be written with base e. Excuse me. So we want to move that e to the 4 up to the top, which makes it an e to the -4. And then my ln and my e cancel, and I'm just left with a -4 from the exponent. Okay. On the next one, I need this to be log base 3 of 3. So I'm first going to rewrite that 9 as 3 squared. And then I want that 3 in the numerator. So when I move 3 squared up to the top, it changes the sign of the exponent, which gives me 3 to the -2. And then my log base 3 and 3 cancel, so I'm left with just -2 from the exponent. Okay? All right, so now what I want to show you how to do is how you can switch forms. So if it's written in exponential form, you should be able to write it as a logarithmic equation. If it's written as a logarithmic equation, we should be able to switch it and write it in exponential form. Okay? All right, so these two are given to us as exponential equations, and we want to write them in log form, which means we shouldn't have things raised to powers, we should have logs. Okay, so just like we did on the practice problems above, we would really like to have the log base and the exponential base be the same, so they cancel. So if I'm trying to get rid of an exponential base x, I need to use log base x to get rid of it, right? And then those will cancel. But if I do log base x on one side, I have to do log base x on the other side. Okay? So log base x of x cubed, the x's cancel, and I'm left with 3 is equal to log base x of 27. And we just leave it like that because we're not solving, we're just rewriting it in a different form. Okay? It was an exponential equation, now it's in a logarithmic equation. Okay? I want to do the same thing on this one. 2 is my exponential base. So to get rid of exponential base 2, we're going to use log base 2 on both sides. So log base 2 of 2 raised to the e raised to the x is equal to log base 2 of 13. My log base 2 and 2's cancel. and I'm left with e to the x is equal to log base 2 of 13. But notice I'm not completely in log form. Even though I have a log, I still have an exponential equation. So I want to get rid of that, right? This is exponential base e. To get rid of exponential base e, I need to use log base e. And remember, log base e is our natural log. So we're going to take the ln of e to the x, and we're going to take the ln of log base 2 of 13. That way, my ln and my e will cancel, and I'm left with x is equal to ln of log base 2 of 13. And now I have an equation that's completely in logarithmic form. Okay, so notice if I started with an exponential within an exponential, I should end up with a log within a log, right, when I change forms. Okay, so this was going from exponential form to logarithmic form. Now we want to look at going from logarithmic form to exponential form. So do you remember when we had that rule? I'm just going to write up here in the corner. Remember when we had that rule that said if we have something like 2 to the x equals 2 to the 5, right? As long as they have the same exponential base, we can just drop those bases. And this meant that x had to equal 5, right? Well, what I'm going to do is I'm going to use this rule backwards because it goes both ways. If I have the same exponential base on both sides, I can't just drop it and be left with the equation that came from the exponent. Or if I start out with some random equation, I can also put in an exponential base and move my equation up into the exponents. Okay, so I'm going to specifically pick an exponential base that I know will get rid of a log. Okay, all right, so let's look at this one. This one's log base 2. So to get rid of log base 2, I need an exponential base 2. So I'm going to put in an exponential base 2 and take this equation, just like I did here, and put it up in the exponent. So that means I have 2 raised to the log base 2 of 1/8 is equal to 2 raised to the negative 3. So notice, whatever equation I had up in my exponent became my equation. I can also take my equation and put it back up in the exponent as long as I do the same exponential base on both sides. So here, whatever my equation was is now up in the exponents of my exponential base 2. And the reason I'm doing this is so that my 2 raised to the log base 2 will cancel. And I'm just left with 1/8 is equal to 2 to the negative 3 power. Okay. All right. I want to do the same thing here. I need to get rid of ln. ln is log base e. So I'm going to use exponential base e and move this up into the exponent. So e raised to the ln of 15 is equal to e raised to the 47, because if I do it on one side, I got to do it on the other. E and ln cancel because they're inverse functions. So I'm left with 15 is equal to e to the 47th power. We just leave it like that. Okay? All right. So we're going to use this idea that logs and exponential functions are inverses to be able to graph logs. Because up to this point, we don't have a way of graphing logs unless we have base 10 or base e, right? Because we have those buttons on our calculator. But what if we want to graph something like log base 2 of x? We don't have a method for doing that. So what I'm going to do is I'm going to start by graphing the exponential form of this. So notice if this is log base 2, the inverse of that would be exponential base 2 to the x, right? And the reason I'm going to start with the exponential is because if I know that the exponential 2 to the x is the inverse of log base 2 of x, remember when we talked about inverses, all we have to do to go from a function to its inverse is swap all our x's and y's. So if I can come up with a table of values for 2 to the x, which I know we can do because we did it in the last section, then all we have to do is swap all of our x and y values, and that gives us a table for the log function. Okay? So that's what we're going to do. We're going to go ahead and put in these exponents. I'm going to go through this kind of fast because we did it in the last section. So 2 to the negative 2 power. The negative is going to flip it the 2 is going to square it. So if I flip it, that gives me a half. I square it, that gives me a fourth. Okay, 2 to the negative 1, that's going to flip it, which gives me a half. 2 to the 0 is 1. And 2 to the first power is 2. 2 squared is 4. All right, so I'm going to go ahead and just graph this so we're reminded of our exponential. Okay, so at negative 2, we're at a fourth. Negative 1, we're at a half. 0, we're up at 1. 1, we're up at 2. 2, we're up at 4. 1, 2, 3, 4. Okay, now this was my exponential, right? And remember the exponential, this is 2 to the x, had an asymptote at y equals 0, right? Had a horizontal asymptote here. So let's look at what happens when we take all of our x's and y's and swap them. So now we have the point 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, 4, 2. So now let's graph these and see what has happened. When x is 1/4, which is just barely past 0, we're down at negative 2. When x is 1/2, we're down at negative 1. At 1, we're at 0. 2, we're up at 1. And 4, we're up at 2. So notice, make this one a little bit bolder. This is log base 2 of x. Okay, so notice when we swap all of our x's and all of our y's, remember it gives us a reflection across the identity line, right? So notice before our y's were coming down and getting closer and closer and closer to 0. So if those y's become our x's, now our x's are coming down and getting closer and closer and closer to 0, right? So that changes this from from a horizontal asymptote to now we have a vertical asymptote right here, where this log is going to get closer and closer and closer to x equals 0, but never touch it or cross it. Okay, so now we have an asymptote at x equals 0. Okay, and if we look at our domain before, right, it went in both directions. All exponentials could keep going, but our domain was based on our x's, right? Our domain now is our previous y's, right? So notice our x's now go and hit this force field of an asymptote right here. So notice my log function can't cross 0 going that direction, right? So it starts at 0 with a parenthesis, and then it continues on out to the right. But our range, which was our original x values, now has no bound, because this is going to keep going down and down and down and down and down, getting infinitely close to 0, but still going down and down and down and down. This side's going to keep going up and up and up, so our range now has no bounds. Okay. All right, so this was an example of a log base where the base was greater than 1. Okay, now I want to look at an example where the log base is between 0 and 1. So if I want to see what the graph of log base 1/2 of x looks like, I'm going to start with the exponential form, which would be 1/2 to the x power. And if I can get a table for 1/2 to the x power, then all I'll have to do is swap all our x's and our y's to get log base 1/2 of x. Okay, so let's go ahead and make our table of values. When I raise 1/2 to the negative 2 power, it means I'm going to square it and flip it, right? If I square it, I get a fourth. If I flip it, I get 4. Negative 1 means I flip it, which gives me 2. Anything to the 0 power is 1. 1/2 to the first power is 1/2. And 1/2 squared is 1/4. So now I'm going to swap it so that I get my log function. Okay. So I have 4, negative 2, 2, negative 1, 1, 0, 1/2, 1, and 1/4, 2. Okay, so I'm not going to graph the exponential. I just want to see what the log looks like. So I'm going to go ahead and graph. When I'm at 4, 1, 2, 3, 4, it's down at negative 2. At 2, we're down at negative 1. 1, we're at 0. 1/2, we're up at 1. and 1/4 we're up at 2. So you can see again, it's going to get infinitely close to x equals 0, right? Because when we swap it, instead of having our y values come down and approach y equals 0, now our x's are getting smaller to come down and approach x equals 0. Okay, so again, notice we still have an asymptote at x equals 0, and our domain still starts at 0, right, and continues on out in the right direction out to infinity. Our range is all real numbers because this is going to keep going up and keep going down. Okay, so what we want to look at now is doing the whole HSRV process. So we're still identifying vertical, horizontal shifts, reflections, and stretching or shrinking transformations, right? But in order to get that starting table for a log, we have to first identify whatever that little base is, make a table for its exponential form, and then once we have the exponential table, we swap it to get our log table. And then once we have our log table, we continue doing our transformations as we always have, okay? So when we do transformations, it's important that we know whether the transformations are happening inside the function or outside the function. So I'm going to go ahead and write, when we have log base a of x, okay? Oops, this is a function, okay? If we have f of x equals log base a of x, okay? If something is happening inside the function, like remember with exponentials, if it was inside the function, it was up in the exponent because that's where the x was, okay? Inside the function for logs means that it's in the parentheses inside the log, okay? So if it's inside the log, then we know that that's affecting our x's, okay? If it's outside the function, meaning it's out in front of this log or outside of these parentheses, then we're going to say it's outside the function, and anything outside the function affects our y's, okay? All right, so let's go ahead and look at one and see if see if we can get this done, okay? So before we start identifying any transformations, the first thing, always first thing I want to do is look at this little base. The little base here on our log, excuse me, on our log is a 3. So that means I want to start by identifying the exponential base 3 to the x, okay? I'm still going to plug in -2, -1, 0, 1, and 2 so that I get a good shape for this exponential, okay? 3 to the -2 gives me 1/9. 3 to the -1 gives me 1/3. 3 to the 0 is 1. 3 to the 1 is 3, and 3 squared is 9, okay? So the whole reason I come up with this exponential version is so that I can swap it to get the log version. So the basic version of this log would just be log base 3 of x, okay? So to get that parent table of log base 3 of x, I'm going to swap these two tables, okay? So everything that was an x is now a y. Everything that's a y is now an x. So we get, not negative, sorry, 1/9, positive 1/9, -2, 1/3, -1, 1, 0, 3, 1, and 9, 2. So this is my log table. So now that I have my log table, I just ignore this exponential table. I don't need to know anything else about that. The only reason I did that is so I could get my log table. Now that I have my log table, I can identify the shifts. So notice the only thing that has changed from this being our basic log base 3 of x function to the function we have here is this one transformation of a -1. And notice that -1 is happening inside the parentheses. So if it's inside the parentheses, we know that's affecting the x's, right? X's are opposite from what we think. So if it looks like we're subtracting one, that's actually going to move us horizontally to the right 1. So we're going to take all of our x's and add 1 to them. And that's the only shift we have on this one. So no stretching, no reflecting, no vertical shifts. So we just need one more table here so that it will now look like log base 3 of x minus 1. And to do that shift to the right, we take the x's from our previous table and just add 1 to them. So 1/9 plus 1 is 1 1/9, right? 1/3 plus 1 is 1 1/3. 1 1 is 2. 3 1 is 4. 9 1 is 10. So we're going to go ahead and our y stay the same. -2, -1, 0, 1, and 2. And now we can plot it to see what our picture looks like. So at 1 1/9, which is just past 1, we're down at -2. At 1 1/3, we're at -1. At 2, we're at 0. At 4, we're up at 1. And at 10, we're up at 2. So it looks something like this, right? And then we just need to identify where the asymptote is. Remember, originally our asymptote was right at x equals 0. So if we move our whole function to the right 1, our asymptote moves with it, right? And our asymptote should now be at x equals 1. Okay, so notice that's where my function's going to start, but it can't touch or cross. So our domain's going to start at 1 with a parenthesis and then continue on out to positive infinity. Our range has no bound, can keep going up and down. Okay, let's look at another one. So really all the HSRV stuff is the same as what we've always done. The only new step is that we have to first identify our log base so that we can get the exponential form, so that we can swap it to get the log parent function. So this is log base 1/2. So we're going to start with exponential base 1/2 to the x power. Plug in -2, -1, 0, 1, and 2. When I plug in a -2 to the power of 1/2, right, that's going to flip it and square it, so it gives me 4. -1 is flipping it to give me 2. 0 gives me 1. 1 gives me 1/2, and 1/2 squared gives me 1/4. Okay, so I'm going to swap it to get log base 1/2 of x. Okay, swap. So now I have 4 -2, 2 -1, 1 0, 1/2 1, 1/4 2. Okay, so this is my basic log function. Now I need to see what transformations have happened to make it go from just log base 1/2 of x to this. Okay, so I actually have two transformations. I have the negative in front of the x and I have the 4. Now normally we see the x written first, so if you want to, you could rewrite this. This is the same thing as log base 1/2 of -x plus 4. So if that makes more sense to you than writing it like this, that's totally fine. Okay? Either way, the negative in front of the x changes the sign of the x's, right? That's a reflection. So if we're changing the sign of our x's, that's going to reflect it about the y-axis. Okay? So that means we're changing our x's. Okay? Then our plus 4 is also still inside the log, right? Because it's inside those parentheses. And inside means we're talking about x's. X's are backwards from what we would think. So that's going to move us horizontally left 4. So we're going to take our x's and subtract 4. So no stretching, no vertical shifts. All right, so let's start with our horizontal shift. So now this looks like log base 1/2 of x plus 4. To do a horizontal shift, we're going to take our x's from the previous table and subtract 4 from them. So 4 minus 4 is 0. 2 minus 4 is -2. 1 minus 4 is -3. 1/2 minus 4 is going to be -3.5. 1/4 minus 4 is -3 3/4. Now, these points are just to help you graph. So if it's easier for you to make these into decimals, use 0.5 and 0.25. That's totally fine, okay? Our y's stay the same, -2, -1, 0, 1, and 2. And now we just need to do our last transformation, which is our reflection. So now we have log base 1/2 -x plus 4. And to do that reflection, we're going to take our x's from the previous table, change their signs. So when I change the signs, they're all going to become positive. So 0, 2, 3, 3.5, 3 3/4, and my y's stay the same. -2, -1, 0, 1, and 2. All right, so let's go ahead and graph it so we can find our domain and range, and also so we can figure out where our asymptote is. So at 0, we're down at -2. At 2, we're down at -1. 3, we're at 0. 3.5, we're up at 1. 3 3/4, we're up at 2. So notice your log is going to come to the side and it's going to bend right at the asymptote. It's either going to bend up at the asymptote or it's going to bend down at the asymptote. So we can see here this one's coming in and it starts bending at 3, starts bending up, right, to avoid the asymptote, which here is going to be at 4, right? We have a horizontal, or sorry, a vertical asymptote. So you can think of like these points are your car. You're driving to avoid hitting a wall. And you just have to figure out where that wall is. So notice it's going from 0 to 2 to 3 to 3.5 to 3 1/4. It's going to start getting closer, closer, closer to 4. Which means that our domain is going to go from back here at -infinity, and it's going to go up to our asymptote, which here is at 4. Our range, excuse me, our range is -infinity to infinity, and our asymptote is at x equals 4. Okay. All right. So I want to do one more, and then I'll have y'all try some. Okay. Let's look at this next one. This next one, first thing I do again is always look at that base. The base here is a 2, so I'm going to start with 2 to the x power so that I can get my parent log. So -2, -1, 0, 1, and 2. When I do 2 to the -2, it gives me 1/4. 2 to the -1 gives me 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. Okay. Then we're going to swap to get our log parent function. So we take all the values and just swap them. So now we have the points 1/4 -2, 1/2 -1, 1 0 2 1 4 2. Okay. All right. Now we need to know our transformations. So I can see 3 different transformations. I can see the 3, I can see this negative, and I can see the -5 inside. Okay. And if you want to rewrite this, you totally can. If it's easier to have the log term first, log base 2 of x minus 5, and then the plus 3 at the end, you can write it like that, or you can leave it like this. Okay. Either way, this positive 3 is outside the log. So we have a positive 3 that we're adding outside the log. That's going to be a vertical shift up 3. So that means we're going to take our y's and increase them by 3. Okay. This negative that's in front of the log is a reflection. So notice that negative is outside the log. That means we're negating our y's. Okay. So if we're negating our y's, that's going to be a reflection about the x-axis. So we're just going to change the sign of our y's because that's where our negative is. And then the last thing we have is the -5 inside the function, right? -5 inside affects the x. X's are backwards from what we think. So that's going to move us to the right 5. So we're going to take our x's and add 5 to them. Okay. All right, so let's make a table for each one. So the first one is a horizontal shift. So now our function looks like log base 2 of x minus 5. And to make that transformation, we're going to take our x's and we're going to add 5 to them. So that's going to give me 5 1/4, 5 1/2, 6, 7, and 9. And our y's stay the same, -2, -1, 0, 1, and 2. Then I'm going to do my reflection. So now it looks like negative log base 2 of x minus 5. And we're going to change the signs of our y's. So now we have +2, +1, 0, -1, -2. And our x's stay the same. 5 1/4, 5 1/2, 6, 7, 9. And then our last is our vertical shift up 3. So now our function looks like negative log base 2 of x minus 5 plus 3. And we take our y's from the previous table and add 3 to them. So that's going to give me 5, 4, 3, 2, 1. Blast off. Just kidding. All right, and then our x's stay the same. So 5 1/4, 5 1/2, 6, 7, 9. So let's go ahead and graph this. So we plot the points at 5 1/4. 1, 2, 3, 4, 5. And 1/4 is just past that. We're up at 5. 1, 2, 3, 4, 5. 5 1/2, we're down at 4. 6, we're down at 3. 7, we're down at 2. And 9, we're down at 1. So it should look something like this. So you can see where our function is coming and curling. It's avoiding hitting this vertical line that should be at 5, right? So our asymptote is going to be at x equals 5. And notice our function starts after the asymptote. So that's going to be from 5 out to infinity. And our range is going to keep going up and down. So -infinity to infinity. Okay? All right. A couple things to note. I want to say this before I forget. On your homework, they're going to have you choose the correct shape. So they have a shape that looks like a log function, and they have a shape that looks like an exponential. So remember, exponentials come down and have a horizontal asymptote. Logs come to the side and curve, which means they have a vertical asymptote. So make sure you choose the correct graph. And then you're going to have to adjust that graph based on your HSRV. Okay? It's not going to require you to type in tables. However, I encourage you to write all of this out and graph it on paper so that you can check your graph on the computer to make sure it looks correct. Okay? So when you adjust it in my math lab, if you need to move it right 5 on the horizontal axis, you're going to take it, should be at 0. You're going to increase it over to +5. Okay? On about the x and y axis, there's a button for a y axis reflection and a button for an x axis reflection. You just check the appropriate one. Okay? And for up 3, again, you have a vertical scale that should be at 0. And if you're going to increase your y's by 3, you'll just move that scale over to +3. Okay? And it should give you the correct graph. But it's always good to go through this process to make sure your graph is correct, because if you graph it wrong on the computer, it's just going to say you're wrong and you're not going to know why. Okay. Also, on the worksheets for both section 5.2 and 5.3, I am grading all of this. I'm grading to make sure you identified your transformations. I'm also grading to make sure you identified all the tables and shifted one at a time to adjust values, and that you drew in your asymptote and identified the domain and range. Okay. All right, so go ahead and pause the video. There's 2 on the next page for y'all to try. Whenever you've done those and you're ready to be checked, or if you get stuck and need help, unpause the video and we'll go over them. Okay, let's go ahead and go over the 2 practice problems. On the first one, you can see that your exponential base is 1/2. So you're going to start with 1/2 to the x power and make your table. Swap it to get log base 1/2 of x. And now you have your log parent table. The only transformation that we have on this problem is the -3 inside, which tells us we're going to shift it to the right. So we're going to add 3 to our x's going to this next table. And then when we graph our points, we should get a log that's been shifted right 3. Okay, so our domain is 3 to infinity. Our range is all real numbers. Our asymptote is at x equals 3. Again, if you were graphing this one on MyMathLab, you would select the graph that looks like a log. So it's either going to look like this or it's going to look like this, right? And then all you're going to do is adjust the horizontal axis to positive 3 to move it to the right 3. Okay? All right, let's look at the second one. The second one has 2 shifts, right? We have the plus 2 on the inside, which moves it to the left 2. So we're going to subtract 2 from our x's. And we have the minus 1 outside the function, which is a vertical shift down 1. So we're going to take our y's and subtract 1. But before we can do that, we have to start with our exponential parent function, which, notice this is a base 5 on our log. So we start with 5 to the x to get the exponential form. Then we swap it so that we have log base 5 of x. And then we can do our transformations. So our first one is the horizontal shift. So we subtract 2 from our x's. And then we do our vertical shift down 1. So we're going to subtract 1 from our y's. Okay. Now I left these in fraction form. If these get really nasty, you can turn these into decimals. So back here when you had like 1 over 25, I think that's like 0.9 or 0.1 something. And then doing 1 over 25 minus 1 should give you negative 1.9. Okay, so if it's easier to work with decimals, feel free to do that. We graph our final table. We should get a graph like this where it's approaching negative 2. Because you can see it's going from huge 23, right, to 3, down to negative 1, down to negative 1, getting closer to negative 2, getting really, really close to negative 2. So we can see that our asymptote should be at x equals negative 2. Because our function's on this side of it, that means we start at negative 2, and then it's going to continue on out to infinity for our domain. And then our range is all real numbers. Okay? All right. So you should now be able to complete the 5.3 assignment on MyMathLab. There's also a worksheet for this section, so make sure you do both. Okay? If you have questions, let me know.